let's look at the fifth one. Let's look at the fifth one. The fifth problem is about a statement Pn which says 1 into 2 plus 2 into 3 plus 3 into 4 plus n into n plus 1 is 1/3 n into n plus 1 into n plus 2. Right? We need to establish this using mathematical induction. So let me assume that Pn is true. This statement is true. Given this true, if I can establish that Pn plus 1 is true, then that will be good. So what is the statement Pn plus 1? The statement Pn plus 1 is like 1 into 2 plus 2 into 3 plus 3 into 4 plus this n into n plus 1, and the term after this, one more term will get added. That means n plus 1 into n plus 2. Right. I want to now show that this is equal to, this is the left hand side for n plus 1. The right hand side should be replacing n by n plus 1. So that's going to be n plus 1. Replacing n by n plus 1. This will become n plus 2. This will become n plus 3 by 3. This is what we want to show. We want to now show that Pn plus 1 must be true, given that Pn is true. Now, look at the left hand side of Pn plus 1. Let's look at the left hand side of Pn plus 1. All terms from here all the way to n into n plus 1 are terms that are part of Pn, right? So this plus this, n into n plus 1, we've assumed is true. That is n into n plus 1 into n plus 2 by 3. So then the left hand side is n into n plus 1 into n plus 2 by 3 plus this term n plus 1 into n plus 2. We take n plus 1 into n plus 2 by 3 common from this. And then we get n here plus 3, which is very clearly n plus 1 into n plus 2 into n plus 3 by 3, which is what we wanted to prove, right? We wanted to, so we have established Pn plus 1. This, if this is true, we have established that this must be equal to n plus 1 into n plus 2 into n plus 3 by 3. That means Pn plus 1 is true. And if Pn plus 1 is true, check for 1. What is P1? P1, the left hand side just one term, 1 into 2, which is 2. The right hand side, put n equal to 1, 1 into 2 into 3 by 3, 1 into 2 into 3 by 3, that makes it 2. So the statement is true for 1, P1 is true. Therefore, because of this relationship, P2 would be true, P3 would be true, Pn in general would be true, right? Right. This one? Okay. See, I'm trying to get n plus, in Pn there are n terms, 1, 2, 3, up to n. In Pn plus 1, in addition there will be one more term. That means the last term would be replace n by n plus 1, n plus 1 into n plus 2. Isn't it? The last term would be replacing n by n plus 1 into n plus 2. And the term before this would be 1 less than this, n, and 1 less than this, which is n plus 1. Do you realize that? That's the sequencing. Do you all understand? Everything here? Clear, no? So replacing n by n plus 1, the last term here is going to be n plus 1 into n plus 2. So now we have 1, 2, 3, n, n plus 1. And the second part of every term is one more than the first part. So the term before this will start with n, and then we'll have n plus 1. Because see, the second term, second factor in each term is one more than the previous factor in each term. Got me? Clear, no? Can I wipe this off? number 6. Pn is a statement which is like 2 into 1 factorial plus 5 into 2 factorial plus 10 into 3 factorial plus n square plus 1 into n factorial. We want to now show that this is equal to n into n plus 1 factorial. We want to show that this is n into n plus 1 factorial. Very clearly. Just be sure about it. The first term starts with 1 square plus 1 into 1 factorial. The second term 2 square plus 1 into 2 factorial. The third term, this 10 is like 3 square plus 1 into 3 factorial. The nth term starts with n square plus 1 into n factorial. Do you understand this sequencing? Now, we will assume that Pn is true. The statement Pn plus 1 therefore is obtained on replacing n by n plus 1. One term will get added to this. Pn plus 1 is like 2 into 1 factorial plus 5 into 2 factorial plus 10 into 3 factorial plus up to this you will get Pn. That is plus n square plus 1 into n factorial plus one term gets added, that is replacing n by n plus 1. Yes or no? Right, so that's going to be n plus 1 whole squared plus 1 into n plus 1 factorial. Yes or no? And we want to show that this must be equal to replacing n by n plus 1 into n plus 2 factorial. This is what we want to show. Yes or no? This is the objective. Clear? So we want to show that Pn plus 1 is true. That means given Pn is true, this statement turns out to be true. That is what we need to set out for. Now, Pn plus 1, left hand side of Pn plus 1. The left hand side of Pn plus 1. Look, terms up to this are terms that belong to Pn, and we have assumed Pn to be true. So this plus this plus this plus this up to this is actually n into n plus 1 factorial, right? And then there is this last term n plus 1 whole squared plus 1 into n plus 1 factorial. Yes or no? We want to show that this is equal to n plus 1 into n plus 2 factorial. Now, one of the things that we learnt in an earlier class was that k factorial is actually k into k minus 1 factorial. Yes or no? Did we learn this? Because k minus 1 factorial would be the product up to k minus 1 into k, that will make it k factorial. Yes or no? Did we learn this in an earlier class? Right? Okay. Now what I do is, from this, I take n plus 1 factorial common. Then I am left with n here. And then this is like n square plus 2n plus 1 plus 1, 2. Yes or no? So this is like n plus 1 factorial into n squared plus 3n plus 2. And do you realize that n squared plus 3n plus 2 is n plus 2 into n plus 1? N plus 2 into n plus 1, that's yes or no? Right? 3n as 2n plus n. You get this, n plus 2 into n plus 1. So this I write as n plus 1 factorial into n plus 2 into n plus 1. Hey, this is 1 into 2 into 3 up to n plus 1, and then into n plus 2. That means this into this will actually be n plus 2 factorial. Yes or no? See, because this is like 1 into 2 into 3 up to n plus 1, and then another term up to n plus 2. That means this into this is 1 into 2 into 3 into n plus 1 into n plus 2. That makes it n plus 2 factorial. Yes or no? This into this will be n plus 2 factorial, right? I'll repeat. See, what is n plus 1 factorial? N plus 1 factorial is 1 into 2 into 3 up to n plus 1. Now, n plus 1 factorial into n plus 2 is going to be what? 1 into 2 into 3 into n plus 1 into n plus 2. And 1 into 2 into 3 into n plus 1 into n plus 2 is product of the first n plus 2 natural numbers, which would be n plus 2 factorial. Right? Right? So, n plus 1 factorial into n plus 2 is going to be n plus 2 factorial. This is going to be n plus 2 factorial into n plus 2 into n plus, sorry, this is n plus 1. N square plus 3n plus 2 is n plus 2 into n plus 1. So, n plus 2 into n plus 1 factorial is going to be n plus 2 factorial into n plus 1 into n, which is the result p n plus 1. So, if the result is true for n, it's found to be true for n plus 1 also. And what is the result for 1? P1 is just first term, which is like 2 into 1 factorial, which is true. What is the right hand side? Right, put n equal to 1. 1 into 2 factorial. 2 factorial is 2. So, the result is found to be true for 1. P1 is true, P2 will be true, P3 will be true, and all Pn will be true. Do you actually understand everything that I have said here? Let's look at 7. Can I wipe this off? Number 7, we have a result Pn, statement Pn, which is like 1 by 1 into 3 plus 1 by 3 into 5. See, these are all odd numbers. 1 by 5 into 7. We want to show is equal to n by 2n plus 1, n by 2n plus 1. Again, like before, we will assume that Pn is true. We will assume that Pn is true. Given that Pn is true, if I can prove that Pn plus 1 is true, then that will be fine, right? So, what is Pn plus 1? The statement Pn plus 1 is like replacing n by n plus 1. One term will get added, right? So, Pn plus 1 would be 1 by 1 into 3, 1 by 3 into 5, 1 by 5 into 7. All the terms up to this, 1 by 2n minus 1 into 2n plus 1, right? And the last term, 1 getting added, see, 2 into n plus 1 minus 1, 2n minus 1, n, right? So, this will become like a 2n plus 1 and this will become 2n plus 3 because this is 2 more than this. So, if this becomes 2n plus 1, this will become 2n plus 3. Yes or no? Because this is 2 more than this. This is 2 more than this. So, if this is becomes 2n plus 1 for n equal to n plus 1, this will become 2n plus 3. So, the last term is 2n minus 1. I am sorry, 2n plus 1. This will become 2n plus 1 into 2n plus 3. We want to show that this is equal to replacing n by n plus 1. This is n plus 1 divided by 2 into n plus 1 plus 1. That's a statement Pn plus 1, which is like n plus 1 divided by 2n plus 3. If I can show that Pn plus 1 is true, given that Pn is true, then our proposition would be taken care of, right? Now, what is the left hand side of Pn plus 1? All terms up to this are part of Pn, which we have assumed is true. So up to this, Pn adds up to n by 2n plus 1. And then the last term is this, 1 by 2n plus 1 into 2n plus 3. If I can show that this is equal to n plus 1 by 2n plus 3, then the result for n plus 1 will be true, right? Now, I take the LCM. LCM is 2n plus 1 into 2n plus 3. So this is n into 2n plus 3 plus 1, yes or no? Clear? This is 2n squared plus 3n plus 1 divided by 2n plus 1 into 2n plus 3. Yes or no? Right? 2n squared plus 3n plus 1. That's the numerator. Now let's factorize 2n squared plus 3n plus 1. This is 2n squared plus 2n plus n plus 1, which is 2n into n plus 1 plus n plus 1, which is n plus 1 into 2n plus 1. Yes or no? So the numerator is n plus 1 into 2n plus 1. Numerator, which is n plus 1 into 2n plus 1 divided by 2n plus 1 into 2n plus 3 will get cancelled, which is n plus 1 by 2n plus 3, causing Pn plus 1 to be true, causing Pn plus 1 to be true. So Pn plus 1 is therefore true. Check for P1. P1 means first term. Left hand side is 1 by 1 into 3, which is 1/3. Look at the right hand side. For n equal to 1, 1 by 2 plus 1, 3. Right hand side is also 3. That means P1 is true, P2 will be true, P3 will be true, Pn will be true in general. True for all n. Mathematical induction. It's called an inductive approach. It's called an inductive approach. When can you apply an inductive approach? When you know the result. It's a check for the result. It's a organized check for a known result. Organized check for a known results. That's mathematical induction. Now, let me just give you another variation around this, which is some divisibility. Can I wipe this off? Let me just illustrate two problems for you. All's good? Can I wipe this off? Look at problem number 9, for example. There is a statement Pn, which for n to be a natural number, 2 to the power 6n plus 3 to the power 2n minus 2, we want to show is divisible by 5. We want to show that this is divisible by 5. Okay. Now, we will assume Pn to be true. We will assume that Pn is true. That means Pn true means that this 2 to the power 6n plus 3 to the power 2n minus 2 is divisible by 5. If it's divisible by 5 means it must be 5 times an integer. If a number is divisible by 5 means that number can be written as 5 times an integer k. K is any integer? Yes or no? A number which is divisible by 5 can be written as 5 times an integer k. Yes or no? Right? Now, given that this is a multiple of 5 times an integer, that's when this will be divisible by 5. I want to show that Pn plus 1, that is replacing n by n plus 1, which is 2 to the power 6 n plus 1 plus 3 to the power 2 n plus 1 minus 2 is also divisible by 5. We want to show this. Given this, we want to establish this. Yes or no? Let's see how we do this. Okay. Now, this left hand side, I want to show is a multiple of 5. Given that this is a multiple of 5, which will cause Pn plus 1 to be true in the event Pn is true, right? Now, this I can write as the left hand side, I can write as 2 to the power 6 into 2 to the power 6n, yes or no? 2 to the power 6 into 2 to the power 6n, laws of indices, plus, bless you, 3 to the power 2n plus 2 minus 2 will get cancelled, 3 to the power 2n, right? Now, what I could do is, this 2 to the power 6n, 2 to the power 6n here, I can write as 5k minus 3 to the power 2n minus 2. The 2 to the power 6n that I witness here, this 2 to the power 6n that I witness here, I can write as 5k minus 3 to the power 2n minus 2, yes or no? So that I can use the statement Pn, so that I can use the statement Pn to establish Pn plus 1, right? This is 2 to the power 532, this is 2 to the power 64, right? This is 64, 2 to the power 6 is 64. 64 into 2 to the power 6n. 2 to the power 6n is 5k minus this. Minus 2 plus 3 to the power 2n. Yes or no? Clear? Now, this is like 64 into 5k. Right? 64 into 5k, already divisible by 5, plus 3 to the power 2n, this is 3 to the power 2n, minus 64 into 3 to the power n minus 2, I hope you realize whatever I have done is, this is 3 to the power 2n, and minus 64 into 3 to the power 2n minus 2 is this, clear? Now this I can write as 64 into 5k. Now from these two terms, I take 3 to the power 2n minus 2 common. From these two, I take 3 to the power 2n minus 2 common, right? Then this will become 3 squared, isn't it? Yes or no? Will this not become 3 squared? I mean, if you take something common, if I take 3 to the power 2n minus 2 common, that means I'm actually dividing each one of them by 3 to the power 2n minus 2. So dividing this by 3 to the power 2n minus 2 would give me 3 square 9, yes or no? 3 squared, because 2n minus 2 plus 2 will give me 3 to the power 2n minus 64. Yes or no? Is that okay so far? You realize whatever I have done here, all of you? This is 64 into 5k. 9 minus 64 minus 55, right? So minus 55 into 3 to the power 2n minus 2. This is divisible by 5. This is divisible by 5. So this whole thing is divisible by 5. Yes or no? That means if Pn is true, Pn plus 1 is true. If Pn is true, Pn plus 1 is true. Yes or no? Yes. Tell me. Right. Good. Very true. Do you all realize everything that I have done? The entire algebra here? See, from these two, when I take 3 to power 2n minus 2 common, this will be 3 square, because 2n minus 2 plus 2 will be 2n, right? And you check for p1, put n equal to 1, what is it? 64 plus 1, 3 to power 0, 1, that makes it 65, which is divisible by 5. So p1 is true. And if p1 is true, given that pn is true, pn plus 1 is true, that means p1 true means p2 must be true, and therefore p3 must be true, and therefore p4 must be true, and therefore true for all n. Yes or no? Similarly, all of you, please try 10, 11 for some time. 10, 11, 12, etc. Stand by.